In today's video, we're going to look at section 1.3, which looks at the intersection point of a pair of lines. So if we are given a pair of lines, an obvious question to ask is, where do they intersect? So we have looked at perpendicular lines, which obviously intersect, and they intersect at a right angle. Parallel lines obviously never intersect, but a lot of other lines will just randomly intersect different angles. And the question is, where do they actually intersect? What is that point of intersection? How do we do this? You've probably done this a lot before, but it is all to do with simultaneous equations. So first, let's assume that we have two different lines that are both in slope-intercept form. That's the easiest kind of scenario that we can have. So assume we have two lines and both of those lines are written in slope-intercept form. Okay. So I'm going to write that as my first line is going to be y is equal to mx plus b, and my other line I'll say is nx plus c. Okay, n would be the slope and c would obviously be the y coordinate of the y-intercept. If I want to find the point of intersection, it's actually very easy when the two lines are already in slope-intercept form. You'll see that both of these lines actually have y on their left-hand side. The right-hand sides are different, but the left-hand side on both of them is y. So to solve them simultaneously, all I would have to do is set the right-hand sides equal to one another. That's the case because they both equal y. So I can set the right-hand sides equal to one another, and at that point I can solve for x. Okay, because the only variable that I now have in that equation is x. M, b, n, and c are all going to be constants. So you can go ahead and solve for x. Once you have done that, you can then just plug that x value back into either one of those equations to find the appropriate y value. Because they will intersect, you should end up with the same y value regardless of which equation you sub that x back into. So you're going to solve for x and then substitute the value back into either equation, and then you're going to solve for y. Okay. We'll do a quick example for this where we have two lines that are both in slope-intercept form. As I said, that's the easiest kind of scenario that you can have. So we're going to find the point of intersection of the two lines. I'm going to have y is equal to negative 2x plus 5 and y is equal to 3x plus 10. Both of the left-hand sides of these equations are the same, therefore I can set the right-hand sides equal to one another, because if they both equal y, they both equal the same thing. So I can say that both of my right-hand sides are equal to one another. At this point, you just have to do some rearranging to solve for x. So I'm actually going to put x on the right-hand side to keep it positive and put my constants on the left-hand side. You can do this however you want. It's completely up to you, and it actually depends on the problem, so it really doesn't matter. But at this point, we just have to rearrange to solve for x. So I'm going to add 2x to both sides. That will leave me with 5 on the left and 5x plus 10 on the right. And then I'm going to subtract 10 from both sides. So that will leave me with negative 5 is equal to 5x, and then divide through by 5, and that will leave me with x is equal to -1. Okay. So I have my x value. Now I need to find my y value that corresponds with that x is equal to -1. Like I said, at this point, you can plug that x value into either one of these equations and you should end up with the same y value regardless of which equation you plug this into. So just for simplicity, because we have a positive coefficient in that second equation, I'm actually going to use this one and plug it into here. As I said, completely up to you which one you want to plug it into. If I do this, I get y is equal to 3 multiplied by my x value, which is -1, plus 10. That's -3 plus 10, which is equal to 7. So the point where these two lines intersect one another, so where they cross over, is at -1, 7. So you have these two lines. One's got a positive coefficient, one's got a negative coefficient, and you find that they intersect at -1, 7. They don't have to have opposite slope, so you don't have to have one's got a negative and one's got a positive. You could just have one's got a much steeper slope than the other line. It just so happens that these two actually have, one's got a positive slope, one's got a negative slope. But either way, they intersect at a particular point, and we found that point by solving these equations simultaneously. Where it gets slightly more difficult is when the lines are not in slope-intercept form. So I'm actually going to do an example when they are in a general form. So we're going to find the intersection point of x plus 4y is equal to 10 and 3x plus 5y is equal to 9. Okay. Slightly more difficult in this case because we do not have the left-hand sides of the equations equal to one another in order to set the right-hand sides equal to one another and solve for x. So we've got to do a bit more manipulation here. Couple ways that you can do this. You can either add and subtract multiples of one equation from another in order to solve, or you can substitute one equation into the other. It is completely up to you. You've probably done a lot of this before, so hopefully we won't need to do too much of a recap, but I will do this a couple different ways just so that you can see what is happening. So first way I'm going to do this is to kind of convert this equation into something where I can add or subtract it to this equation. So let's start out with, I've got x plus 4y is equal to 10 and 3x plus 5y is equal to 9. What I can do is actually multiply this first equation through by 3. Why would I do that? That would make my coefficients of x the same. If I then subtracted one equation from the other, I would be left with something just in terms of y's and constants and could go ahead and solve for y. I'm not changing the equation in any way by multiplying it through by a value because I can always simplify it by dividing through by that value again. It's just basically making the equation slightly more complicated, but it simplifies our problem overall. So if I go ahead and multiply that first equation by 3, remember to multiply every term by 3. So I get 3x plus 12y is equal to 30. It's exactly the same as my equation 1. It is just making it a slightly more complicated equation by multiplying it through by this value. And then I'm going to keep my second equation the exact same. What you should now see is that we have a 3x for both of these equations. So if I subtract the second equation from the first equation, you'll find that I get something in terms of just y's and constants, which makes this much easier to solve because at this point, all I have to do is divide through by 7 and I get my value for y. So this is very convenient, especially if you have one of your variables in one of your equations actually has a coefficient of 1, like we had for x in our first equation here, because then you can just multiply that equation through by whatever the coefficient is in the second equation, multiply that whole equation through by that value, and then subtract one equation from the other. Now we've got our y value, I'm just going to plug that into one of these equations and solve for x. Again, you can plug it into whichever equation you like, it doesn't matter. You can plug it into the first or the second equation, you should end up with the same x value regardless. So if I do that, I'll plug it into the first equation. I get x plus 4 multiplied by 3 is equal to 10. So x plus 12 is equal to 10, subtract 12 from both sides, I get x is equal to negative 2. So my point of intersection is negative 2, 3. Okay. Another way that I could have done this is by taking that first equation and rearranging it and then substituting it into my second equation. Okay, that would have been another way to do this. So you'll notice that for my first equation, I've got x plus 4y is equal to 10. I could have made that look slightly different and said that x is equal to negative 4y plus 10. So all I've done is subtract 4y from both sides. Again, still the same equation, I've just manipulated it slightly. At that point, I have x in terms of y. I can substitute that into here, and then my second equation would just be in terms of y. So if I did that, I would get 3 multiplied by this value that I had for x. So my value for x was negative 4y plus 10. And then I've got plus 5y is equal to 9. Okay. If I distribute this out, I get negative 12y plus 30 plus 5y is equal to 9, which gives me negative 7y plus 30 is equal to 9. I'm then going to subtract 30 from both sides. And then I divide through by negative 7. That still gives me the exact same y value that I got when I did this the first way around. So this was, we'll call this A. This was the first way that I did this, part A, was just by saying, okay, I'm going to multiply one of these equations by a value, makes the equation more complicated, makes my problem more simple. I'm going to subtract one equation from the other, I'm able to solve for y, I substitute that y value into one of the equations and I'm able to solve for x. My second way of doing this, we'll call it B, is by rearranging my first equation in terms of x. So I've got x is equal to something in terms of y, and then I was able to substitute what I have found for x into my second equation, which gives me an equation solely in terms of y, and then I'm able to solve for y. At this point, it is exactly the same as we did in situation A, where I plug that y value of 3 into either one of these equations, and I'll get that same value for x. So the second part of this is exactly the same. The other way that you could have done this, which is more complicated, and I probably wouldn't recommend doing this unless it's like part of a problem where they have asked you to do this, is if you actually manipulate both of these equations to put them into slope-intercept form. So I have started with two equations that are in general form. Okay, these were my two equations. Both of these are in general form. What I could have done instead is to manipulate these to be in slope-intercept form. So we did this in a previous section. So all you're going to do is manipulate these so that both of them have y on the left-hand side and then something in terms of x plus a constant on the right-hand side. I'm not going to go ahead and do that as we have done it before, but if you did that, your equations actually become, the first equation is y is equal to negative 1 over 4x plus 5 over 2, and your second equation becomes y is equal to negative 3 over 5x plus 9 over 5. Okay. So you have these two different equations that are just manipulations of my original general form equations, but now they are both in slope-intercept form. At this point, you can do exactly the same as we did in the first example, and you can make the right-hand sides equal to one another and solve for x. So I can go ahead, set those equal to one another, do some manipulation, and solve for x. Once you have solved for x, you'll take your x value, plug it into either one of these equations and find the appropriate value for y, and you should end up with the exact same answer of negative 2, 3 being the intersection point that we did before. Okay. So that's kind of three different ways of doing this if you are given an example where your lines are not in slope-intercept form. Now we're going to relate what we have just done to something that you can find in economics, which is looking at the price point of something relative to the quantity of that particular thing that is available. So we're going to say that the price of a particular unit of something, whatever this thing may be, the price is going to be denoted by P. Okay, price is going to be denoted by P. That is the price per unit of the particular thing that you are selling. The quantity that you have, so the quantity of this particular thing that is available, is going to be denoted by Q. And we're going to look at a couple of different ways of relating these two things. So how price per unit of something relates to the quantity of that particular thing that is available. Okay. I'm going to plot Q on the x-axis and P on the y-axis. So whenever you plot these, you should see that the quantity that is available is always going to be plotted on the x-axis, and the price is going to be on the y-axis. This kind of makes sense because y is normally a function of x, especially when you look at a slope-intercept form of the line. The y value depends on the x value. So the price will depend on the quantity of a particular thing that is available. So we'll look at two different things. We're going to look at a supply curve and a demand curve. A supply curve is looking at this situation from a manufacturer's point of view. So we're going to look at this particular quantity and price situation as though we are the manufacturer. The greater the quantity that we have to supply, the higher the price per unit, okay? Because we're going to require more time, more labour, more materials. All of these things are going to play into my price point. So if I'm the manufacturer, the more quantity of these things that I have to make, the higher the price point. That means that my supply curve is going to have a positive slope. The higher the quantity that we need to have available, the higher we need to make the price point per unit, because we need so much more time and labour and materials in order to make a higher quantity of these things. The demand curve is actually looking at this as though we are the consumer. So it looks at the relationship between the quantity and the price from the consumer's perspective. Okay. And again, I'm going to plot out my X and Y axes where my price will depend on the quantity. If we are the consumer, in order to buy a higher quantity of these things, we want the price point for each unit to be lower, okay? If the price point is higher, we are less likely to buy more of these things. So for a larger quantity to be bought by a consumer, you need the price point per unit to be lower. That means that the demand curve is actually going to have a negative slope, okay? Because the higher the quantity bought means that the price point per unit has to be lower. So they've got this negative relationship. So our supply curve is going to have a positive slope as the more things that you need to produce means that you have to put the price point higher for each item. And for the demand curve from the consumer's point of view, for us to buy more of a particular thing, we need the price point per unit to be lower, which means that we have a negative slope. When you are looking at a particular item, whatever that might be, it could be something in the grocery store, it could be anything, building materials, absolutely anything that you find. In order to see how much needs to be produced and the price point that we should have for each item, we need to actually use these supply and demand curves and find their intersection point. That intersection point is actually called the equilibrium point where supply equals demand. It means that the quantity produced will stabilize. So you are making enough of the product that people are buying it, but you're not making so much of the product that you're going to end up with a bunch of these items left that no one's buying, but you're also producing enough to where you actually have enough for people to buy and you're not going to have a shortage of something. So this equilibrium point really is helpful when you are looking at how much you need to produce of a particular item and also the price point that you need to have in order for people to actually buy the item, so that it's not too cheap where you can't cover expenses, but it's not too expensive to where people aren't actually buying it. Okay. There is an example on page 22 of the textbook. It's example 5, and it actually goes through finding this equilibrium point, this intersection point. I'm going to talk through it very quickly, but it's just a real world example of what we have just done. So it's example 5 on page 22. It gives you a supply and a demand curve. Okay, so it looks at the price point for something in terms of the quantity. So it's given you actually 2 equations that are in slope-intercept form. It then wants you to find this equilibrium point. Okay, so it wants you to find the price point that we need to have per item and also the quantity that needs to be produced of this particular item. So they have set the right-hand sides equal to one another. They have solved for Q, so they have found the quantity, which is exactly what we did before, where we had our example where we set the right-hand sides equal to one another and we solved for X. Okay. Then what they've done is they've taken that quantity, which is 5,000, and they have plugged it in. And they found that the price point per unit has to be $3. Okay. So it's exactly the same as what we have done before. It is just a real world example of using these supply and demand curves and using these intersection points. And it's a very good lesson in economics, actually, where this is a real world example. So I highly recommend you go ahead, look through that example again, and make sure that you are comfortable with this before we move on.